And this is a vapor-liquid equilibrium problem with two components, 1 and 2, that are initially in the vapor phase, but we want to keep compressing that vapor phase until it's completely condensed. The vapor has 30% of the first component and 70% of the second. And you're given information on the saturation pressures of each component, and also given information on what the bubble pressure is of a 50-50 mixture of components, and that's just a little bit over a bar. And so part A says estimate the pressure required to completely liquefy the 30-70 mixture, assuming that we can use the one parameter Margules equation. All right, so this is a simple activity coefficient model. All right, and one thing that's nice about the system that we currently have is that we can assume it's low pressure, so we can assume an ideal gas. And that means that we should be able to write expressions of the form y1p is equal to x1 gamma 1 p1 sat. And another modified Raoult's law expression where we just change the subscripts to correspond to component 2. So what we're going to need in order to solve this problem ultimately are the activity coefficients. And one thing that's convenient to do, since we actually are given a data point, so we're given for a 50-50 mixture, so for some different compositions, we know what the total pressure in the system is, which suggests that it might be convenient to actually sum this up to remove one variable, which is the vapor phase mole fractions. Right, and that will be equal to x1 times p1 sat times the activity coefficient for component 1 plus x2, so saturation pressure for component 2, times the activity coefficient for component 2. All right, and we have values for all of these, so we know what the bubble pressure is, and the bubble pressure is 1.08 bar. And the bubble pressure, remember, is the pressure at which you have the final bubble of a vapor that's being condensed all the way to liquid. And so the composition of the total system is equal to the liquid composition. Composition of the total system in this case is 50-50. Right, so now we have gamma 1 and gamma 2, one equation and two unknowns. We're going to use the one parameter Margules equation in order to convert these two unknowns into the single unknown, which is that one parameter of the equation. Right, and so we'll go ahead and re-express this. The one parameter Margules says that we can determine the activity coefficients for our two components in terms of this single parameter times the mole fraction of the other component squared. Right, we can take the exponential of both sides in order to solve for the activity coefficient, and we can plug it into the expression we had on the first page. So we have the exponential of a to the x2 squared, which is x2 is 0.5 here, and the exponential of a again to the 0.5 squared because x1 is also 0.5 for the bubble pressure. We can then use that to collect terms and solve for this exponential term, which shows up twice, exponential of a to the 0.5 squared, and that's equal to 0.785. And then we can solve for a, and that is equal to negative 0.97. Right now, we want to go back, and what the problem actually asks us is to estimate the pressure that we need to completely liquefy that mixture, the 30-70 mixture. And so we now have our activity coefficient model, and we just need to determine what the pressure is, the bubble pressure is for that system. At the bubble pressure, the system composition is equal to the liquid composition. And so we're solving for the bubble pressure, and that's equal to, in this case now, we have 30% component 1 times 0.82 bar. And now we take the exponential of negative 0.97 times 0.7 squared, because we have 70% of component 2, which goes into our Margules equation. And then add to that 0.7. That's 1.93 bar. Times the same exponential term. But now we have 0.3 squared. So 30% of component 1. This allows us to solve for the bubble pressure, which is again what we're looking to solve for here, which is equal to 1.39 bar. Now for part B, there are a number of ways to answer this if we go back and look at the problem statement. So if we clearly here don't have an ideal solution, for an ideal solution gamma is equal to 1. Right, so we know we don't have an ideal solution. Right, but would the required pressure, if it were an ideal solution, be greater than or less than the one that we just solved for this non-ideal solution? So it says explain in terms of molecular interactions between components 1 and 2. And so in this case, if we go back and look at what we solved for, we found that the value of A, in this case, is negative, and a negative value of A is going to cause our gamma term, when we take the exponential of ax squared and these kind of terms, to be less than 1. All right, so our activity coefficients are less than 1. All right, and if our activity coefficients are less than 1, that means that we're in our modified Raoult's law expression, if we just write that again here. If this is less than 1, then we'll be exerting a lesser partial pressure than if gamma was equal to 1. Right, so we're saying gamma is less than 1 for this non-ideal solution, but if it were an ideal solution, then gamma, the activity coefficient, would be equal to 1. And so we would be exerting more pressure. And this makes sense in terms of the interactions between the molecules in the liquid phase, because this negative value indicates an excess Gibbs free energy that is negative, so a negative contribution to that. So there are stabilizing interactions between the liquid phase components. They are attractive to each other, and they attract each other more than they are attractive to themselves. Right, so they exhibit net attractive interactions, and because of these attractive interactions, it's harder to make stuff go into the vapor phase. Right, and so therefore, the pressure for an ideal that is required in order to compress an ideal solution completely into the liquid is greater than the pressure for this Margules case, for the real solution. So another way of looking at it is that a gamma less than 1 indicates that the molecules are happier being in the real solution than they would be in the ideal solution because of the attractive interactions, and therefore it's not as hard to compress them completely out of the vapor and into the liquid. So therefore it takes more to compress them for the ideal solution case than for the one parameter Margules case that's described here.